Welcome. My name is Thomas and I'm studying computational science with emphasis data science. My project is the Perona Malik equation. I solved the Perona Malik equation with the Mimetic method. So the Perona Malik equation is an anisotropic diffusion process. It is a nonlinear diffusion, and it actually does, it blurs or denoise areas in an image which have to be a bigger likelihood not to be edges. And this is the equation. So this is the partial derivative of I over t, and that is equal to the divergence of c multiplied by the Laplacian of I. So c is the diffusion coefficient, I is the image, and the diffusion coefficient is this equation here at the bottom. The diffusion coefficient depends on the gradient of I and the sensitivity to edges. This parameter I had to find later in my algorithm, and here you can see just another form of the equation. So the initial condition and the boundaries. Here on the left side you can see the input image, and here the noisy image. That is the image I gave as input to see if the equation, if my algorithm is really working. So to denoise at the end. And the image is 512 by 512 pixels. And I use Neumann boundaries. That means that there is no change around the boundaries. And how did I implement that? I added another layer of pixels around the whole image, and the value of those pixels is the same like the outermost pixel value of the image. So now, how did I implement it? Here's the equation again, and I defined the mimetic operators like the divergence operator, the gradient operator, and then I used them. So I first reshaped my image, I got a vector, then I calculated the gradient for the actual image, so for each iteration I did that. And then here is the diffusion coefficient with k equals 7, and then at the end we add it to the actual image, and then we reshape it back to a 2D image. And that is actually the whole calculation. So this part is actually in a for loop. So for each iteration we did this whole calculation. Then, my results. First, I had to find out which is the best amount of iterations for my algorithm. I measured the peak signal to noise ratio, and as you can see here, 90 iterations should give the best output. And here are my outputs. On the left side is the noisy input image. Then we have here 50 iterations, 90 iterations, and 140. And here on the bottom you have some parts of my images, so you can see better what the algorithm is really doing and how then the output is. So you can see 50 iterations, the image still has some noise, and with 90 iterations it is much better. There's still a bit of noise, but compared with 140 iterations, where we lost some image information and also the edges are not anymore that sharp. So 90 iterations is actually the best output of those three. And that's actually already the end of my presentation. Thank you for listening.